Alright, in this video we're going to first prove the alternating series test, and then from this proof as a direct consequence of our argument we'll have proven what's known as the alternating series estimation theorem. Alright, so let's start with the proof. As we'll see is nice and visual. You can see this number line here where I've marked off 0. Now one thing I want to note is that since the b sub n's are non-negative and they're decreasing, if one of our b sub n's were equal to 0, since they're decreasing, that would imply that all subsequent terms would also be 0. So in fact, our series would just be a finite sum, in which case it would certainly converge. Okay, so for the more interesting case, let's assume that the b sub n's are strictly positive numbers and they're decreasing. Okay, now for the first partial sum of our series, this is just going to be b1. And I'll mark that in the picture here. So S1 is B1. And now for the second partial sum, S2, I want to subtract B2 from B1. So that's going to move us to the left on the number line. Now the question is, how far to the left can I move? Well, the fact that the sequence B sub n is decreasing says in particular, B2 cannot be larger than B1, meaning that I cannot move further to the left than where I started. In other words, I cannot move to the left of 0. So let's say we land here. Okay, here's S2. All right, now for the third partial sum, I want to add B3. That's going to move me to the right. How far can I move to the right? Well, again, from this condition, I know that B3 can be no larger than B2, meaning I cannot overshoot this partial sum S1. So let's say we land here. Now I'm just going to keep going, right? I'm going to subtract B4, and I know I cannot overshoot this partial sum S2. Okay, so on each stage, okay, one of two things is possible. If it's the case where I have equality in this condition, like let's say B2 is equal to B1. Well, if that's the case, then I'm just going to undo what I did on the previous stage, right? So I'd add B1, and then I'd just be subtracting B2, which would really just bring me back to 0. Okay, so that is a possibility. But see, from this second condition, and this is where this condition is necessary, B sub n is approaching 0. So while I might undo what I just did on the previous stage for some of these iterations, okay, eventually things do have to narrow down, right? And so if I repeat this process, there will be a narrowing down to some limiting value, and I'll call that limiting value S. Okay, so in other words, the sequence of partial sums, S sub n, does have a limit, and so by definition that implies that our series converges. All right, so that's the proof, the alternating series test. And now what I want to point out from this picture here is that we have the following inequalities, right? So if I look at the gap between S, this limiting value, and the first partial sum S1, okay, notice that it is no larger than B2, right? This distance in red, okay? Notice that S minus S2, well, that's the gap between our limiting value S and S2. Okay, that gap can be no larger than B3. Okay, likewise for S minus S3. Okay, that gap can be no larger than B4, so on and so forth. So the gap between S, the limiting value, and S sub n, the nth partial sum, this gap can be no larger than b sub n plus 1. Okay, so what I want to do is summarize this. This is what's known as the alternating series estimation theorem. Okay, so let S equal our series. So there's really S value is just the sum of our series. And here we're assuming that this series satisfies those two conditions on the alternating series test. Okay, so if S sub n denotes the nth partial sum of this series, then we have that S minus S sub n in absolute value is less than or equal to b sub n plus 1. Okay, so why is this a nice result? Well, if I want to approximate this series with, say, S3, so in other words, I want to add up just the first 3 terms of this sum to get an estimate for the value of the series, I'd like to have some idea of the size of the error in my estimation. And that's exactly what this quantity in the absolute value is telling me, right? S is the actual value and S sub n is the approximation. So this gap is really the error in this approximation. And this inequality says, and this is what I'm saying here in yellow, that the error is bounded above by the first discarded term. So if I use S3 to approximate this series, so B1 minus B2 plus B3, notice the first discarded term would be this B4. Okay, and this result is saying, hey, your error can be no larger than that first discarded term B sub n plus 1. Okay, so in the next 2 videos, we'll look at some examples of how to apply this result. All right, well, that's going to do it for this video. Thanks.